In this lesson, we discuss some approaches to determining how to make an appropriate assumption about whether a population is normal. Let's recall the central limit theorem for means. We know that if the sample size is large, then everything is awesome sauce, and we can go on to use the central limit theorem in more advanced statistical procedures. But sometimes we're stuck with small samples. When this happens, we can either throw up our hands and say, "That's too bad, it can't be done," or we can explore other ways to proceed. The central limit theorem for means works for small samples, as long as it can be reasonably assumed that the population is approximately normal. So how do we go about making this assumption? Basically, it comes down to this. The more normal the sample looks, the more reasonable the assumption is that the population from which it was drawn is normal. So if we see things like outliers, strong skewness, or multiple modes in the sample, then those things might also appear in the population, meaning that it's probably not normal. Let's keep these three things in mind. Generally speaking, hard and fast rules don't work well here. Often, we may need to take more than one approach to settle on whether or not we're making a reasonable assumption. We're not seeking perfect normality. In fact, what we're doing is proceeding with the assumption that the population is approximately normal, and then observing the sample to see if there are any features that would cause us to abandon that assumption. Determining whether the population is approximately normal is most important when we have small samples. If the sample size is large, then the central limit theorem already applies. Okay, so let's begin with a data set that is highly skewed to the right. These data are a sample of 20 wind speeds in miles per hour recorded at the time of alleged Bigfoot sightings. One tool that we can use to look for outliers, skewness, or multiple modes is a strip chart, also known as a stacked dot plot. A strip chart simply indicates where each data value falls on an axis by plotting a point. For data values that repeat, the points stack on top of each other. Let's look at a strip chart for the Bigfoot wind speed data. Know that there appears to be an outlier in the right tail. Another tool we can use is a histogram. Again, it seems that there is an outlier. The histogram also gives us a better idea about the degree of skewness. Based on what we see so far, it seems unlikely that the population from which the sample was drawn is approximately normal. Okay, I'm going to generate some data that I know is normal. I'm going to use the command rnorm and, mean, sd, which creates a set of n values that come from a normal distribution with a given mean and standard deviation. We'll compare the strip chart and histogram for the normal data to the skewed data that we've already observed. Note how in the strip chart the points are more spread out, and I don't see any evidence of outliers or strong skewness. These same features seem to occur in the histogram. Again, I don't see any evidence of outliers or strong skewness. Now, keep in mind that we are examining a small sample, which is only a fraction of the whole population, and therefore we may not have enough data for the histogram to form that classical bell shape. The goal here, though, is to check to see if there's anything significantly different from a normal curve that would call into question the assumption of normality. Think of it like working a puzzle. There may be some pieces that haven't been filled in yet, but you might still be able to imagine the overall image. Okay, we're going to jump into an example. A fish hatchery raises trout to stock streams and lakes. The weights in ounces of a sample of 18 trout at their time of release are as follows. We want to know, is it reasonable to treat the sample as coming from an approximately normal population? Let's start by loading the data into a variable named trout.weight. Now I'm going to take this approach of assuming that the population of trout weights is normal unless I see something in the sample that causes me to abandon that assumption. Okay, let's take a look at a strip chart of the weights. Note how most of the values are in the middle of the distribution with fewer values towards the tails. Overall, I don't see anything here that causes me to abandon my assumption of normality. Let's also construct a histogram just to get a different take on the sample. Well, the histogram doesn't exactly look normal, but remember, the sample is only a small slice of the population. I mean, here there are only 18 values, and the majority of them still fall within the middle of the histogram. So again, I'm not seeing anything here that makes me think that this sample might not be coming from a normal population. An alternate method for identifying normality is a normal quantile plot. This is a scatter plot that shows standard normal percentiles on the x-axis and the corresponding ordered values from the dataset on the y-axis. If the data are normally distributed, the scatter plot should closely resemble a straight line. Now, when it's not normal, there are certain patterns that we might watch out for. But keep in mind that randomness sometimes obscures things, especially when we're dealing with small samples. In R, the QQNorm command creates a normal quantile plot. We can also add the QQLine command, which would demonstrate what exact normality looks like. Let's create a normal quantile plot for the trout weights. Note how the points do not deviate significantly from the line, indicating, in agreement with what we've seen before in the strip chart and histogram, that it seems reasonable to assume that the population is approximately normal. Okay, let's jump into another example. Here we're going to import a dataset consisting of characteristics of a population of irises. Now what we'll do in this example is take a sample of two different variables and make a determination about the assumption of normality for each. Then we'll take a look at the actual population, just to see how we did. Okay, we're going to take a sample of the lengths in centimeters of sepals, a part of the flower that supports the petals when it's in bloom. Let's investigate whether it would be a reasonable assumption to treat the population of sepal lengths as approximately normal. I'm going to create a strip chart, a histogram, and a normal quantile plot. In this strip chart and histogram, there doesn't appear to be any evidence of strong skewness or outliers. The normal quantile plot demonstrates points that do not differ significantly from the line. Based on what we can see in these plots, it appears that it would be a reasonable assumption to believe that the sepal lengths population is approximately normal. Okay, well now let's check it. We've got the population, so let's take a look at the histogram. A histogram of the entire population of sepal lengths show that the population is indeed pretty close to being normal. Let's do a similar investigation with iris petal lengths. We take a sample of petal lengths. And then we'll create a strip chart, histogram, and a normal quantile plot. Now in each of these plots, we can see elements that call into question the assumption of normality. Skewness and possible multiple modes seem visible in the strip chart and histogram. In the normal quantile plot, note how the points differ quite a bit from the line. In this case, it seems likely that the population of petal lengths is not normal. We can confirm this by observing the entire population of petal lengths. Okay, in this lesson we examined methods for determining if it's appropriate to assume a population is normal based on what we see in a sample. However, assumptions always carry a risk of error. Luckily though, most statistical methods are relatively forgiving, even if the population is slightly non-normal. Unless there are factors that call for stricter evaluation, it's generally acceptable to be somewhat more tolerant in making our normality assumption. In other words, we'll look for cases of strong skewness or obvious outliers, or in the case of a normal quantile plot, points that are a clear deviation from a line. There are other methods for testing the normality of a population, but we'll have to get a little further down the road before we can get into those.